Hello and welcome back to this video series about the Intermediate Math League of Eastern Massachusetts. Today we're going to be starting the number theory section for Meet 3, so let's get right into it. So there are two main concepts in number theory Meet 3 that show up a lot, and scientific notation is the first one. So that's what we're going to be starting with. So what is scientific notation? Well, scientific notation is a way of simplifying large numbers to be written as a times 10 to the power of n, where a is greater than or equal to 1 and less than 10, and n is an integer, which means it has no fractions or decimals. So some examples of scientific notation are these numbers below. 12,340 can be written in scientific notation as 1.234 times 10 to the power of 4. 7 can be written as 7 times 10 to the power of 0. 0.5 can be written as 5 times 10 to the power of negative 1. And 14 million can be written as 1.4 times 10 to the power of 8. So the reason that scientific notation is helpful is because we can express all of these numbers, these large numbers, all in a way that we can compare them very easily. For example, this number, 14 million, is a really, really big number. And sometimes it's difficult to wrap our head around a number that big, especially if it asks us to multiply 14 million by another number or add it to another number. But by writing it in scientific notation, we simplify it down to 1.4 times 10 to the power of 8, which allows us to compare it easily to other numbers such as 7 times 10 to the power of 0 and 5 times 10 to the power of negative 1. Now, to explain why these numbers are written in scientific notation properly is because if we look at our definition, it says to be written as a times 10 to the power of n, where a is this first number here that I'm underlining. So in these respective cases, it's 1.234, 7, 5, and 1.4, where a is between 1 and 10, and it can be equal to 1. So all of these first numbers, 1.234, 7, 5, and 1.4, are between 1 and 10. And then n is an integer, which is the power of 10. So in all these cases, where n is 4, 0, negative 1, and 8, it's an integer because it doesn't have a fraction or decimal. So now we need to talk about how we actually write numbers in scientific notation, which is, remember, a times 10 to the power of n. So to explain it, I'm going to have actually two different examples where I'm going to be writing 0.541 and 43,900 in scientific notation. So in order to write these two numbers in scientific notation, we have two values to find, the value of a and the value of n. And the first one that you should find, which is always the easier one, is the value of a. So the way you find the value of a is you have to think about the fact that a is going to be in between 1 and 10. Now, when you multiply anything times 10 to the power of some number, or 10 to the power of n, all the digits are going to stay the same. For example, if I multiplied 3.21 times 10 to the power of 2, which is 100, then all the digits would actually stay the same. It'd be 321. And all the digits also stay the same relative to each other, which means that when you create this number, a, that's between 1 and 10, you're going to have the exact same digits. So what does that mean in these examples? Well, in this example, my value of a, if I were writing this in scientific notation, would be 5.41. Because all the digits stayed the same and stayed the same relative to each other, except now I turned 0.541 into a number between 1 and 10. And in this example, 43,900, when I write it in scientific notation, the value of a will be 4.39. And all the digits stayed the same and stayed the same relative to each other. Now you might be thinking why I didn't include the zeros at the end of this. Now it's 4.3900. Now the reason I didn't include the zeros is because when you have them at the end of a decimal, so in this example I have both of the zeros as the last digits in my decimal, they actually make no difference to the value of the decimal, which means if I excluded these, it wouldn't change the value of my number here. Now, it is different if you have a decimal like this. Say my decimal is 0.309, then the 0 does matter because it's in between two significant digits, or digits that determine the value of this decimal. But when they're at the end of the decimal all by themselves like this, you can just cross them off because they're not going to make a difference to the value of that decimal. So my values of a for these examples were 5.41 and 4.39. Okay, well then the next step is to find the value of n. And remember, n has to be an integer, which means it can't have any fractions or decimals in it. So the best way to find the value of n is think about how many places you have to shift the decimal point over. And what I mean by that is in this example, 0.541, in order to turn it into 5.41, I shifted the decimal point one place to the right. Because now if my decimal point, instead of being behind the 5, is right here, then that turns this number into 5.41. And in this example, where I had 43,900, and in a number where you don't have a decimal point is actually at the end right here. In order to turn that into 4.39, I shifted it over once, twice, 3 times, 4 times. So if my decimal were here, it'd become 4.3900, and then those zeros don't matter at the end. So I shifted this one 4 times to the left, so 4L, and I shifted this one 1 time to the right. Now, when you shift the decimal point one place to the right, that means you're going to have, or when you shift the decimal point to the right, that means your value of n is going to be negative. So right means you're going to have a negative value of n. And if you shift your decimal point to the left, that means you're going to have a positive value of n. And the reason why is because 10 to the power of negative 1 as an example equals 0.1. And if you think about it, if I multiplied 5.41 times 0.1, that would turn it into a smaller number, turn it into a decimal. And that's exactly what we have here, a smaller number. And if I multiplied 4.39 times 10 to the power of 1, which is 10, that would turn it into a bigger number. And what we have here is a bigger number. So that's why when you shift the decimal point to the left, your value of n is going to be positive, and when you shift it to the right, it's going to be negative. Now, since I shifted it to the right 1 time here, then my value of n is going to be 1. But since it's to the right, that means it's actually going to be negative 1. And in this example, since I shifted it to the left 4 times, that means my value of n will be 4. And since it's to the left, it's a positive 4. So in these examples, when I finally finish my scientific notation, which is the last step, and combine the numbers you already created, then this example is 5.41 times 10 to the negative 1. And this example is 4.39 times 10 to the power of 4. And if I write these out of scientific notation, so this is correct, but if I wrote it out of scientific notation, just to make sure you understand, this looks like this, 5.41 times 0.1, because 10 to the power of negative 1 is 0.1, and if you multiply this out, you get 0.541. In this example is 4.39 times 10,000, because 10 to the power of 4 is 10,000. And if you multiplied 4.39 times 10,000, that gets you 43,900. So your 3 steps: find the value of a, which is going to be the same digits except between 1 and 10. Find the value of n, and you find that by figuring out how many places you shift the decimal point and in which direction, figure out whether it's positive or negative, and what your value of n is actually going to be. And then you just combine those 2 values into the scientific notation proper form to finish your scientific notation. All right, so now I have a review question about writing numbers in scientific notation. If you'd like to try it, I'll give you a few seconds to pause the video and then I'll explain the answer. So the correct answer to this question was 5.0041 times 10 to the power of 3. So our 3 steps in finding scientific notation for a number is to find the value of a, which I'm going to write as the first step. Then we want to find the value of n, and then we combine them together to finish the scientific notation, which I'm just going to write an F for finish. So find the value of a, find the value of n, and then finish the scientific notation by using your values in the proper form. So remember, a has to be between 1 and 10, right? So if I write this out, it's going to look like this. A is greater than or equal to 1, and a is less than 10. So the number we have here is 5,004.1, which is way bigger than 10. But remember, when we find the value of a, we keep all the digits the same and the same relative to each other, which means it's still going to have a 50041 somewhere in this value. Now, the first non-zero digit is a 5, which means that our value of a is going to start with 5. And since 5 is in between 1 and 10, then it's going to be 5.0041. Because now I have all the digits relative to each other the same, and all the digits are the same, except now my value of a is between 1 and 10. And remember, these zeros, since they're in between two other digits that are significant, which means they're not 0, and even though they're in the decimal point, I don't have to cross them off because they actually matter in this example. So my value of a is 5.0041, so I'll check that off. Now I need to find my value of n. So how do I get 5004.1, which I'll write out, to 5.0041? I have to shift the decimal point over, right? My decimal point starts here. I need to get it to here because that creates it as 5.0041. So in order to do that, I shift it 1, 2, 3 places to the left, which I'll write out as 3L. Now, when you shift to the left, if you remember, that means your value of n is going to be positive. When you shift to the right, it's negative, and when you shift to the left, it's positive. So my value of n is going to be positive. And since I shifted it 3 times to the left in order to get it to 5.0041, then it's going to be a positive 3 because I shifted it 3 times. So my value of n is a positive 3. So a is 5.0041, and I'll check n off, and n is positive 3. And so now if I combine it in my scientific notation to write it in the form of a times 10 to the power of n, then that gives me 5.0041 times 10 to the power of 3. So this is my answer here. Now for IMLEM Me3 and number theory Me3, you don't just have to know how to write scientific notation, but you also need to know how to do operations on them, and specifically how to multiply and divide numbers in scientific notation. And in order to learn that, there's a few basic concepts that we need to know about powers in the commutative and associative properties of multiplication. So first we're going to talk about how multiplying and dividing different powers of the same numbers work. So if I have the multiplication of a to the power of n and a to the power of m, then my answer is going to be a to the power of n plus m. And if I have the division of a to the power of n and a to the power of m, then my final answer will be a to the power of n minus m. Now that can be a little bit confusing because I have a lot of variables here, a, n, and m, which show up a bunch of times. So let me give you a more practical example. If I had 10 to the power of 3 and 10 to the power of 5, and I'm multiplying them by each other, well, if I look at my multiplication example where it says where I have a to the power of n times a to the power of m, where a is the same number both times, so I'm using 10 both times, 3 and 5 would be my n and m because those are the powers of the first and second number. So if I multiply these out, then it's going to give me a to the power of n plus m. For 10, which is my a, to the power of 3 plus 5, which is my n plus m. So 10 to the power of 3 times 10 to the power of 5 actually leaves me with 10 to the power of 8 because 3 plus 5 is 8. And the same applies to division. If I had 10 to the power of 5 divided by 10 to the power of 3, again, 10 is my a, and it's the same number. This only works if you have the same number with your powers. And then my n is 5, because that's the first power. My n is 3, because that's my second power. So therefore, a to the power of n minus m is my answer, or 10 to the power of 5 minus 3 equals 10 to the power of 5 divided by 10 to the power of 3. And that gives me 10 to the power of 2. All right, the second concept you need to know in order to multiply and divide scientific notation is about how the commutative property and associative property of multiplication works. So because of the commutative and associative property of multiplication, if you're multiplying or dividing two scientific notations, so I have two scientific notations here with variables, a times 10 to the power of n and b times 10 to the power of m, and then here I have a times 10 to the power of n divided by b times 10 to the power of m. They can be written out like this, where I have a times b times 10 to the power of n times 10 to the power of m. And when I'm dividing them, I can write it as a divided by b times 10 to the power of n divided by 10 to the power of m. And the reason why this works is because with multiplication, it doesn't matter what order you do it in. And with the associative property of multiplication, you can shift around the parentheses as long as you're ending up with the same operations. So here, when I divide a by b, I'm still multiplying the numerators by multiplying it together, and I divide 10 to the power of n divide by 10 to the power of m, which means I'm actually doing the same operations. Now, what does this look like in practice problems, and why can this help us solve scientific notation, multiplication, and division problems? So here I'm about to show you two different problems where I actually apply this in order to understand how this works. So the first one is 3 times 10 to the power of 2 times 5 times 10 to the power of -1, and it wants me to multiply these two scientific notations by each other. So what this tells us is when we have our two scientific notations multiplied by each other, we can turn it into a times b times 10 to the power of n times 10 to the power of m. So in these examples, my a is 3 and my b is 5, because those are the first numbers in both scientific notations. And then 10 to the power of n is 10 to the power of 2, and 10 to the power of m is 10 to the power of -1, because those are the first and second 10 to the power of whatever numbers in my scientific notation. So if I were to change this up and write it in the form that makes it easier to multiply, I could write it out as 3 times 5, because that's my a times b, so 3 times 5 times 10 to the power of 2 times 10 to the power of -1. And the reason this makes it a lot easier to multiply these scientific notations is because now you can do 3 times 5 really easily, that's just 15, and then you can use the trick I taught you where you add or subtract the powers to multiply the powers together. So if I multiply 10 to the power of 2 and 10 to the power of -1, then I have to add 2 and -1, and since 2 plus -1 is 1, because it's the same as 2 minus 1, then it's going to be 10 to the power of 1 when I multiply those out. So therefore, my final result is 15 times 10 to the power of 1. Now, this is equal to the correct answer, but a lot of questions will ask you to write this in scientific notation. So you still need to be able to figure out how to convert these numbers back into scientific notation. Because if you'll notice, I have 15 as my first value. And my first value in scientific notation needs to be between 1 and 10. So the way I do that is the exact same way I would normally do it. I figure out where the decimal point is, and I figure out where I need to shift it to, just here, because that'll make it into 1.5. And since I shifted one value to the left, then I add 1 to my power. So that gives me 1.5 times 10 to the power of 2 as the answer to 3 times 10 to the power of 2 times 5 times 10 to the power of -1. Now, if I'm going to do my next problem, which is a division problem, where I have 9.2 times 10 to the power of 4 divided by 2.3 times 10 to the power of 5, then I have to write it out in the exact same way in order to simplify it. So a times 10 to the power of n divided by b times 10 to the power of m equals a divided by b times 10 to the power of n divided by 10 to the power of m. So what this means is in these examples, 9.2 is a, 2.3 is b, 10 to the power of n, which is the one that shows up in the first parentheses, is 10 to the power of 4, and 10 to the power of m, which shows up in the second parentheses, is 10 to the power of 5. So if I follow my equation and write it out, this gives me 9.2 divided by 2.3, and then times 10 to the power of n, which is 10 to the power of 4, divided by 10 to the power of 5. And yeah, I just noticed that I used different division signs here. That was an accident. These both mean the same thing. Okay, so one trick I do want to teach you when you end up with decimals in your equations is you can actually remove the decimals and then put them back if you need to in your final answer. And what I mean by that is when you convert this to 9.2 divided by 2.3, I can actually change this to 92 divided by 23. And the reason this works is because I'm dividing 92 and 23 and 9.2 and 2.3. I just multiplied both of these by 10, right? 9.2 times 10 is 92. 2.3 times 10 is 23. And when I divide that out, since I multiply them both by 10, since 10 divided by 10 is just 1, it doesn't change my answer. So now if I divide 92 by 23, which is a little bit of an easier question, if you solve it all out, it'll be 4. And now I have 10 to the power of 4 divided by 10 to the power of 5. And remember, when you divide two numbers where you have your two powers, 4 and 5, and they're two powers of the same number, then what you need to do is subtract your numbers by each other. So 10 to the power of 4 divided by 10 to the power of 5 equals 10 to the power of 4 minus 5. And 4 minus 5 is negative 1. So then 10 to the power of 4 divided by 10 to the power of 5 equals 10 to the power of negative 1. And now if I finish my scientific notation, it gives me 4 times 10 to the power of negative 1. And finally, I have a review question on multiplying and dividing scientific notation. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll go ahead and explain the answer. So the correct answer to this question was 3.6 times 10 to the power of 1. And this was actually a difficult one, but I'll show you how to solve this question. So first I want to simplify the numerators and denominators. I have multiplication of scientific notations in both of them, and I know how to simplify that, right? So 5.4 times 10 to the 13 times 1.4 times 10 to the negative 6 can be written as 5.4 times 1.4 and then times 10 to the power of 13 times 10 to the power of negative 6. So now I'm multiplying together my powers of 10 and I'm multiplying together my regular numbers that don't have any powers, right? So I can break it up into that, but I actually want to do one more thing to this expression. I want to get rid of the decimal points because we don't like decimal points. Decimal points make equations kind of messy and a little bit hard to simplify, right? It only says write your result in scientific notation. So I can actually take this out of scientific notation and then put it back in when I find my result. So I want to get rid of these decimal points. And the way I'm going to do that is by multiplying by a power of 10. So if I multiply 5.4 by 10, which is 10 to the power of 1, and I multiply 1.4 by 10, which is 10 to the power of 1, that gives me 54 times 14. And you might notice I just randomly multiplied by 10 to the power of 1 twice in this equation. And that means that this expression isn't going to stay equal. Now the way I can solve this is if I multiply 10 to the power of 13 by 10 to the power of negative 1, and multiply 10 to the power of negative 6 by 10 to the power of negative 1 as well, that offsets these 10 to the power of 1s. These 10 to the power of 1s and 10 to the power of negative 1s offset each other and cancel each other out. So I can turn this into 54 times 14 times 10 to the power of 12 times 10 to the power of negative 7. Now, what I did might have been a little bit confusing, but essentially what I did is I multiplied by a power of 10 to get rid of these decimals and divided by or multiplied by a negative power of 10 to decrease my powers of 10 that I already have in order to make sure this expression stays equal. So now I have 54 times 14 times 10 to the power of 12 times 10 to the power of negative 7. Well, now I'm going to simplify my denominator. So I actually want to get rid of this 3.5 and 3.5 times 10 to the negative 14. I want to get rid of the decimal point specifically. So in order to turn this to 35, I have to multiply by 10 to the power of 1, right? Because that gives me 35. In order to offset that, if I multiply my 10 to the power of negative 14 by 10 to the power of negative 1, which means it's going to be 10 to the power of negative 15, that actually doesn't change the value of this expression. So now I have 35 times 10 to the power of negative 15 times 6 times 10 to the power of 19. And if I group that together, I have 35 times 6 times 10 to the power of negative 15 times 10 to the power of 19. Okay, I know it doesn't look like I simplified this much, but we're actually so much closer to the answer now. And the reason why is because now that I simplified it like this, is because I can break it up into two sections. I can break it up into my regular numbers without powers, 54 times 14 divided by 35 times 6. And then I can break it up into that and my powers of 10 times 10 to the power of 12 times 10 to the power of negative 7. And then that's divided by 10 to the power of negative 15 and times 10 to the power of 19. And the reason that you can break it up like this is because we have all multiplication in our numerator and all multiplication in our denominator. So you can actually break it up into whatever fractions you want as long as you're multiplying the same numbers in the numerator and the same numbers in the denominator and multiplying in between. So I broke it up into two separate fractions, this one and this one, and now I can simplify both of them except each individually. So if I simplify my powers of 10, I have 10 to the power of 12 times 10 to the power of negative 7. And since I'm multiplying these, I add my powers together. So 12 plus negative 7 is 5. So my numerator is 10 to the power of 5. And then that's divided by 10 to the power of negative 15 times 10 to the power of 19. Since I'm multiplying these, I add my exponents together. Negative 15 plus 19 is 4. So then I have 10 to the power of 4 in my denominator. And now I have 10 to the power of 5 divided by 10 to the power of 4. And since I'm dividing, I subtract my second number, 4, from 5 to give me 10 to the power of 5 minus 4, which is 10 to the power of 1. So this whole mess simplifies to 10 to the power of 1. All right, now I have to simplify this section. Now I can actually break this up into even more fractions, and I'm actually going to do that in order to show you a concept called cross-canceling. When you're only multiplying in both the numerator and denominator of a fraction, you could do something called cross-canceling, which is when you cancel out specific terms in order to reduce your numbers. And this is what that looks like. If I cross-cancel this, I can turn 54 into 9 and 6 into 1. And I can turn 14 into 2 and 35 into 5. And let me show you why I can actually do that. It's because if I broke this up, and I'm going to undo all these. So if I broke this fraction up into two separate fractions, like I did when I had this big one, I can break it up into 54 divided by 6 times 14 divided by 35. Now, why is this important? Because if I broke it up into these two and simplified each of these individual fractions, this leaves me with 54 divided by 6 equals 9. And if I wrote that in fraction form, that's 9 over 1. And if I wrote this in fraction form, 14 divided by 35, that leaves me as 2 divided by 5, or 2/5, because 14 divided by 35 is 2/5. Now, this is the concept of cross-canceling. You see how I broke these up in separate fractions and then divided them individually? Well, I actually can still do that, except I don't have to break it up into separate fractions. 54 divided by 6 is 9. So if I divide each of these by 6, 54 divided by 6 is 9, and 6 divided by 6 is 1. Then I can simplify this to 9 and 1. And then 14 divided by 7 is 2. 35 divided by 7 is 5, because they both have 7 as a common factor. So if I divided those two by 7, that gives me 2 and 5. And so that's what I did here. When I broke it up into 54 divided by 6 and 14 divided by 35, I got 9 over 1 times 2 over 5, and I did the same thing here. I just cross-canceled it without breaking it up. So now I have 9 times 2 divided by 5 times 1. And this is why I chose to make these not decimals, because it's easier to cross-cancel when you don't have decimals. So 9 times 2 is 18. 5 times 1 is 5, so that gives me 18 divided by 5 times 10 to the power of 1. So now if I divide 18 by 5, I'm going to write that in decimal form in order to make sure it's in scientific notation. If you divided that out, that would give you 3.6. So my final answer is 3.6 times 10 to the power of 1. And I know I just introduced cross-canceling to you. I probably should have introduced it a little bit earlier because it's a little bit complicated, but I really just want to go over it one more time to make sure you're not left confused as to what I did here. So if I had 9 times 4 divided by 3 times 2, well, obviously I can multiply this out. 9 times 4 is 36, 3 times 2 is 6, and 36 divided by 6 is 6, right? So this equals 6. Now, I could also cross-cancel this. And the way it works is by breaking it up into two fractions that divide really easily. What I mean is if I broke it up into 9 divided by 3 times 4 divided by 2, and remember, you can only do this when you have multiplication only in both the numerator and denominator. So if I broke it up into 9 divided by 3 times 4 divided by 2, which will give me the same answer, now I can simplify this really easily. 9 divided by 3 is 3. So if I simplify that into a fraction, it's 3 divided by 1. Because if I divide both my numerator and denominator by 3, because that's their common factor, then that gives me 3 and 1. And the common factor of 4 and 2 is 2. So if I divide both the numerator and denominator by 2, in the numerator, that gives me 2. In the denominator, that gives me 1. So now I turn this into 3 times 2, or 3 over 1 times 2 over 1, and that gives me 6, right? Cross-canceling is when you do that, except you don't actually break it up into separate fractions to save time. I can still divide 9 and 3 each by 3 separately and get 3 and 1 here. And I can divide 4 and 2 by 2 separately from 9 and 3 and get 2 and 1 there. And that's cross-canceling. When you divide one number in both the numerator and denominator by a common factor, just to simplify what you're multiplying and what you're dividing. And that's what I did here when I divided 54 and 6 both by 6 and 14 and 35 both by 7, because they had those factors in common. That's the idea of cross-canceling. That's why I brought these out of decimal form, and I really hope that was a good explanation of what I did here. All right, now to quickly review what we learned this lesson. So we learned what scientific notation is, which is when you write a number as a times 10 to the power of n, where a has to be in between 1 and 10, and n has to be an integer. These were some examples of scientific notation, and the reason why we write in scientific notation is because it allows us to simplify how we write large and small numbers, and then compare them more easily and do operations on them more easily with each other. Next, we learned how to write numbers in scientific notation, which is 3 steps: find a, find n, and then write out the scientific notation in proper form. So the way you find the value of a is just by creating the number that's in between 1 and 10, but has the exact same digits relative to each other. So 0.541 becomes 5.41, and 43,900 becomes 4.39. Then you find the value of n, which is, and the way you do that is you figure out how many times you shift the decimal point over in order to get your value of a from the original number. If you shift it left, then your value of n will be positive, and if you shift it right, then your value of n will be negative. Now, we also learned that how many times you shift the value of the decimal point is what your actual absolute value of n will be. All right, next we did a review question where we wrote 5004.1 in scientific notation, which gives you 5.0041 times 10 to the power of 3. Next, we learned how to multiply and divide with scientific notation. And in order to do that, we had to learn a few basic concepts. First, when you multiply and divide powers of the same number, and it has to be of the same number, when you multiply them, you add the exponents together, and when you divide them, you subtract the exponents from each other. And then we learned that when you have scientific notation and you multiply and divide them, you can actually group together the first two terms, your a in both of them, or I used a and b in these examples because they're different scientific notations. And your second terms, which are your powers of 10, and when you multiply them, you multiply those two by each other, and when you divide them, you divide those two by each other. And then we did 2 examples where we did this one and this one, which had multiplication and division in order to demonstrate this concept. And then finally, we did a very difficult review question where we simplified this mess into 3.6 times 10 to the power of 1. And in the process of that, I did my best to show you how cross division works. All right, so that's all I have for today's lesson. I hope it is helpful. I know some of this stuff was really confusing, and I might have made it a little bit confusing by introducing cross-canceling in the final question, but I really hope I explained it well, and I really hope you get the basics of scientific notation. I'll see you next time.